Let's go for it. It is my great pleasure to introduce Camille Carpentier today from University of Namur, who's going to give us a talk which title is slightly different from what I thought it was, but that is perfectly okay. A reinterpretation of the link-species relationship connects ecosystem structure and stability. And just not to put any more pressure on, me just say that when I first heard about this project, my mind was blown, but no pressure and no biases for how it's going to go. With that, the floor is yours, Camille.
How do I handle that now? Okay. Hello, everyone. Thank you for this great introduction, Yuri, and thank you for having me in this theoretical ecology seminar. It's kind of the first time that I talk about this really like with a crowd of theoretical ecologists. Most of the time I try to communicate that with people who do not do theory. So it's kind of a little bit new for me, but I hope that you will that I will manage to make you find this interesting. So today we're going to talk about three main questions in theoretical ecology. And the first one is the really well-known question, will a large complex system be stable? That was asked by May in the 70s. And you probably all know these questions that has led to a lot of different studies and this complexity stability debate that has been going on for a few years now. And the second question I'm going to address today has been asked 10 years afterwards by Cohen and Bryant, and they talked about how does the total number of links in a web vary as the number of species increases. And this question also led to a lot of different studies. And the last question I'm going to talk about today, which also is a really important question in theoretical ecology and has been raised more recently, is how correlated or independent are the various components of stability. This is a question that was asked by Danu et al. In 2013, and that is basically based on the general idea that because we measure so many different components of stability, so many components of complexity, we might be a little bit lost in those plethora, and maybe trying to find links between different components of stability of ecosystem will help us to understand what really shapes this stability. And therefore, we have here three questions that most of the time are in fact addressed separately while they are intrinsically linked to each other. And I'm going to try to explain to you how looking at all those questions together allows to better understand these questions and maybe the answer we could find for those questions. So firstly, we're going to look at a large complex system and can then be stable. So the question May asked in the 70s was about local stability. And to really like make a quick summary of what local stability is, it's the capacity of the system to recover from a small change in species densities. So if the system is capable of going back to its previous state, so its previous densities equilibrium, then it's considered as locally stable. And if the perturbation spreads in the networks and the change in density becomes bigger and bigger over time, then we say the system is not stable. And you can look at local stability by looking at the real part of the right most taken value of the community matrix at equilibrium. And what May showed by looking at this local stability is that the link, for the number of links and the species richness have a negative impact on local stability. So basically, when you increase the number of species in a web, it's going to be locally less stable. And if you have more connected web, they're also less stable. And a lot of studies have worked on this basis that is based on random matrices. And the general idea here is that when people look at these questions, most of the time they don't take into account the fact that in fact the number of species impacted the number of links. And this is the question asked by Cohen and Bryant: how does the number of links changes when the number of species changes? And what you can say is that basically when you add a species to a system, it has to link to the species that are in the system. And therefore, you have a positive relationship between the number of species and the number of links. And this relationship has been modeled as a power law that I'm just going to explain afterwards. But the general idea is that we are looking for the parameters allowing to understand the shape between the species richness and the number of links. And this is the link-species relationship. And all the studies about the link-species relationship try to answer the question asked by Cohen and Bryant in the 80s. And so here you can see the link between the first question and the second one. And then we have a third question, which is how correlated are the various components of stability? And if we want to understand that, what we need to do is looking at various components of stability. And so today we're going to also look at robustness. And robustness can be defined as the fraction of species you have to remove to lose 50% of your initial number of species. And it has been shown in the literature, when you look at topological robustness, that increasing the number of links in a web will increase the robustness. So basically, the most connected you are, the less you're going to be impacted by species removal, basically because species can compensate the loss of their prey or their partners by interacting more with the remaining prey or partners. And so here what you can see is that because the number of links have a negative effect on local stability and a positive effect on robustness, maybe there is a link between the two. And maybe we can find an equation that links the two. And if we do so, then we would be able to predict local stability based on robustness. And that would help to answer the question asked by Denou et al. By showing that at least those two components of stability are highly connected. And what I'm going to do today is show you how those questions are linked and end up with an analytical expression of local stability as a function of robustness, and show to you that we can link indeed those two measurements of stability, and this by using the link species relationship. So I'm going to start by explaining this and how our approach allows to in fact connect the whole diagram that I just showed you before. So let's start with this first question. How does the total number of links in a web vary as the number of species increases? Since the 80s, people have tried to answer that question by using this equation, where L is the number of links and S is the number of species. In this presentation, I'm going to define the number of links as the number of edges in a network and the number of species as the number of nodes in a network. And what people have tried to do is find the value of A and B, and most effort have been in fact done on the value of B, because it's really what is going to shape the relationship. And in the literature, you can find kind of two schools. You can say either B equals 1, and then you have a linear relationship between the number of links and the number of species, or B equals 2. And then you have S that's scaled with S squared. And then the general idea is that it's a constant connectance hypothesis. And so you have different hypotheses about the value of B, and people have tried to really understand this value to be able to link the number of links and the number of species. And when you do so, what you do is looking at this kind of graph where you plot the number of links as a function of the number of species. And what people have done so far is going on the field and record the number of links and the number of species in one system. And when that is done, they're going to go on another ecosystem and sample the number of links and the number of species. And then you can do that a certain amount of time, and you end up with different points, and you have a shape that is starting to be drawn in this LS plane. And what people have done so far to find the interaction, well, the relationship between L and S is in fact to do log L log S regression. So basically, if you take the logarithm of L here and of S here, what you can see is that B is in fact the slope of this relationship. And when you do so, you end up with, so you can make a linear regression in the log L log S space, and then you can end up, for example, with this curve that allows to predict, based on the number of species, the number of links you have in your system. When you do so, you end up with one value of A and one value of B for all systems. And this is kind of important to say, because it means that, let's say that my first ecosystem is a marine food web, and that my second system is a terrestrial food web. When I draw a line between these two systems, the general idea that I can apply is that I have the same relationship between the number of links and the number of species in my two systems. And it's kind of, therefore, implying that A and B are in fact universal. And if A and B are universal, as for example, Martin has hypothesized in 92, then we should have the same value of A and B over all the different data sets we use and different studies we use. And when you look at the relationship you can find in the literature, what you can see is that in fact we don't have the same relationship between these different throughout different data sets. What you can see is that we don't have the same relationship between the number of links and the number of species. And this leads to kind of a conclusion that is different than A and B are universal. And moreover, we have seen in the literature that the value of B can be affected by different parameters, such as the habitat constancy, the habitat type, the spatial scale, and the interaction type. So all those evidence that maybe, in fact, the value of A and B are not universal, but they might be, in fact, network specific. And this is the hypothesis we did by reinterpreting the question asked by Cohen and Bryant. And the general idea here is that you have here the question, how does the total number of links in a web vary as the number of species increases? And we kind of said that what they mean by in a web is in fact in one web. And if you ask the question, how does the number of links change in one web when the number of species changes, then you are assuming that A and B are network specific, so that you can find one value of A and one value of B for one network, as you can compute connectance, linkage density, or those metrics for one network. So the general idea here is to stop trying to find a universal relationship, but kind of zoom in the network and see if we can find in a network, how does the number of links changes when the number of species changes. And to do so, we're going to start with a toy network here, where you have 6 nodes and 15 edges, so 6 species and 15 links. Basically, all the species interact with each other. And what you can do is then plot this possibility here on this graph. So basically, 6 species, 15 links, I have 1 point on my graph. The problem is that we don't want 1 point, we want multiple points to be able to make a regression and find a relationship. And that's why people most of the time go on another network and try to find a relationship between the number of links and the number of species by going on different networks. But we want to stick in the same network. So how do we make S vary and L vary inside a network? Well, just like let's make S vary by removing a species. And then here you remove a species and you have 5 links that are removed. So you have a new point on your graph. And then you can remove another species, another one, and another one. And then you end up with this possibility here where removing a species will just lead to no network anymore. So we stop the decomposition over there. And when you do so, you do what we call network decomposition. And so when I'm going to talk about network decomposition, I talk about this process of removing species and recomputing the number of links and the number of species at each step. And when you do so, what you can see is that you're going to have a relationship between the number of links and the number of species, and that this relationship is specific to this network. And we have here, how does the number of links vary in one network? Now we can look at another network, like a network with only specialist species. And then here we have 6 species, but only 3 links between them. And then you can be, okay, let's remove a species and see what happens. So we remove a species, and interestingly, here what happens is that we have a secondary extinction. The number of species is going to decrease faster than in the fully connected case, just because here the general idea is that if I remove this species, then the second one is left without any partner, any resource, and is going to go extinct. And so we have a secondary extinction. And then we can remove another species and we have another secondary extinction. And therefore you can see that only 3 steps are needed to end up with a network that we cannot decompose anymore. And this is obviously to toy with extreme cases, but obviously you have intermediate cases where you have different number of interaction between different species. And so in that case, you will have multiple possibilities. So the general idea is that you will have different trajectory that are possible in the LS plane, because when I'm going to remove a species, for example, a top species like this, if I remove this species, then I lose the species and 3 links, and I have 1 point here. But if I start by removing a basal species, then I will lose its consumer and also the links that consumer adds. And so we are on another point on the graph. And you can see that we can have a lot of different combinations possible of the order we can use to remove species, and to not have to do that by hand, we decided to perform in silico extinction experiments. During this in silico extinction experiment, what did we do? We just randomly remove 1 species, then see if there is any secondary extinction. If there is a secondary extinction, we're going to see if this extinction cascades further. So if we have maybe a 3rd extinction, a 4th extinction, so we do that until there is no extinction anymore. And then we compute the number of links, we compute the number of species, and we remove a new species. And we really do this a couple of times, even more than a couple, like a lot of times, to end up with a relationship between the number of links and the number of species in the network. The rule we choose to perform secondary extinction was a species goes secondary extinct when there is, well, it has no resource left or no link left. So here the general idea is that the no resource left makes sense. For example, if a predator doesn't have its prey, it might die. If a plant does not have its pollinator, it might also die. But the no link left is in fact an hypothesis that you can release. So the general idea is that what the result I'm going to show today are about the fact that when a species is not connected to any other species, we just considered it's not in the network anymore. But you could decide that, for example, when you remove the predator of a prey and the prey has no link with the rest of the network, it's still in the network because it was like the prey does not depend on its predator for its survival. And so this last hypothesis that a species go extinct when it has no link left can in fact be released. And I have an equation for that in the appendix slide. So if you want to see the results for that case, I have them. It's just that the equations are easier if you just say when a species is not connected anymore, it's not part of the network anymore. But we can work around that hypothesis. Okay, so now that we know what we're talking about, we performed in silico extinction experiments on almost 500 empirical networks taken from different web databases. And what we did is end up with networks with an average number of species that was 35 and the maximal was 250 species. And I'm going to show you the results for example, this network that is less a toy network and more a realistic network where you have 166 species. And what you can do is remove those species. And when you do so, then you end up with a relationship between the number of links and the number of species. And you can see that this relationship is here the results of 10,000 decompositions. And it's a power law. So because it's a power law, what you can do is make a linear regression in the log L log S space, and you can find the value of B and the value of A. But the big difference with what I just talked about before, the classical approach, is that this value of A and this value of B are for this network and not across different network. It's in this network, when you remove species, when you change the number of species, here is how the number of links is going to vary. And you can use this equation to find this dotted line that is now on the slide. And this dotted line allows to predict the relationship between the number of links and the number of species with a really good R-square. So we are quite good here in predicting how the number of links changes when the number of species changes in one web. However, this approach is really time consuming because you have to do 10,000 decomposition, and for each decomposition you have to go until you have no species left, for example. So it's really time consuming, and we also thought it was not really kind of useful if you cannot compute B like let's say easily, like you can compute connectance or linkage density. We really wanted something that we can compute easily. And therefore we tried to find a way to express B as a function of the initial number of species and the initial number of links. So basically as a function of these numbers here. And to do so, what we did is zoom in a little bit in this graph. And if we zoom here, what you can see is that we have different dots size here. And the size of the dot is the likelihood that this combination of number of species and number of links is observed when you decompose your network. And for example, when you have 6 species, you can either have 3 links, 4 links, 5 links, or 6 links between your species. And the case where you have 6 links is less likely to happen than the case where you have 4 links between your species, for example. And in fact, it's not the 6 species case that is interesting, it is the 2 species case that is interesting, because what you can see is that when you have 2 species, well, basically, when you have 2 nodes in a network, you have only one edge between them. You can not have more and you cannot have less. You cannot have more because it's edges, and you cannot have less because then it's not a network anymore. And so the general idea here is that we can, in fact, root our relationship at the s equals 2, at equal 1 points. And you can, in fact, do that for any networks, because if you look at this toy network that I showed previously, you can all see that it's also root to 2 species, 1 link. And this is because this is the smallest decomposition possible for any network. And so when you know that, you can say, okay, let's anchor our relationship to that point, and then you can express A as a function of B. And this is interesting because then you end up with this equation. And this equation is useful. Why? Because you can then rewrite it as B is the logarithm of the initial number of links in the network and the logarithm of the initial number of species in the network. And then you can compute B based on L and S and plugged into this equation, and then you make vary the species richness, and you will see how the number of links changes. So if I take the example with our big network here, the general idea is that you have 166 species and 319 links. And so what you're going to do is say, okay, I'm computing my B based on this equation. Let's do it. I have a B of 1.304. And then I put this 1.3 value here in this equation, and then I make S change and I see how L changes. And when you do so, you end up with this black line, solid line here that is really close to the dotted one. And the dotted one is the one you obtain when you make the regression. So in fact, the B we find is really close to the one from the regression, and you can test that for this network, but in fact, you can test it for all or 500-ish network. And here is the graph of B computed with this equation as a function of the slope of the regression computed on 10,000 in silico extinction experiments per network. So basically here, 1 point is one network. And the dotted line is the identity line. And what you can see is that here we have a kind of a good relationship between B and the slope of the regression. They are really close to each other. And what we wanted to also test is not just the fact that B can kind of replace the regression, but also that we still predict well the relationship between the number of links and the number of species. And so in this case, what you can see is that we end up with an R-square of 0.99. So we have a really good R-square still, even if we do not do the regression, but use this equation. And we compute the R-square for all our 500 networks. And we ended up with this graph where you have the number of networks. And here is the R-square. And you can see that for most of our network, we have an R-square that is higher than 0.8 and even higher than 0.9. And so you really have a good predictive power of those two equations. And based on that, we were like, okay, so to the question, how does the total number of links in a web vary as the number of species increases? The answer is, well, at least an answer can be, well, the number of links increases with the number of species based on a network-specific parameter that we can find. And this network-specific parameter is B, and B is defined as a function of species richness and number of links, and allows to explain how does the number of links changes in a web when the number of species changes. And now you're like, okay, cool, but how does this help with, for example, robustness? Well, people that have already worked with robustness should have recognized an expression that I use, which is in silico extinction experiments. So B allows to compute how the number of links is going to change when you remove species. But therefore, it should also be able to predict how the number of species changes when you remove species. And this is basically the process that is behind robustness, right? Because robustness, the general idea is how many species do I have to lose to remove a fraction of my species. And so if we can predict how the number of species changes when we remove species, then we can predict robustness. And how does the number of species changes? We're going to compute that with the mean number of species lost. So mean delta S is, as we defined it, the average number of species you lose when one species is removed. So delta S is going to be 1 when there is no secondary extinction, because when you remove a species, the system has lost one species. And when you have secondary extinction, then the delta S is going to be higher. And then you can also express the mean delta S as the slope of the NR relationship, where N is in fact the number of species lost, and R is the number of species removed. And you can see that this is the case, well, this is a graph for the 166 species network that I showed you before. And what you can see is that it's a linear relationship, and we're basically going to try to find the slope, the mean slope of this relationship. And to do so, we're going to work with the variation of the number of links, because we know that B allows to predict this variation. And in fact, if you assume that the number of species you lose on average is small compared to the total number of species you have in your web, which will be the case for large web, then you can express this variation of the mean number of links as this equation. And in this equation, the mean delta S is the mean number of links lost when one species is removed. And in fact, when one species is removed, what you lose is its outgoing links, but also its incoming links. And so what you lose when you lose one species is in fact 2 over LS. And then you can replace mean delta S by this expression, and you end up with this, where you have the mean number of species lost when one species is removed can be approximated by 2 over B. And we were like, okay, this is nice, but it's a little bit too simple. Probably it's not the case. So let's check it, right? So what we did is having our number of species lost, our number of species removed, and just say that the number of species lost is 2 over B multiplying the number of species removed. And we tried to see if it did work with our in silico extinction experiments. And here are the R-square we obtained. So for most of our network, you can see that our R-square is quite high because we are higher than 0.7. And so we're like, okay, cool. So this simple expression seems to work. Let's see how it gives us information about robustness. In fact, robustness is just one special case of the relationship between the number of species lost and the number of species removed. Because the question, when you look at robustness and you define it as the fraction of species to remove, to lose 50% of the initial species, basically you're looking at this dotted line here, that is 50% of the species has been lost, and you want to see the intersection of this line with here each decomposition. And if you want the average, then you can just look at the intersection between the dotted line and the solid line, and the solid line is just saying that the slope of this line is 2 over p. And so we just want the intersection between the two lines. So this is a really simple equation, and then you can find the value of robustness. And the value of robustness is b over 4. Again, we were like, this is too simple. Let's check it. And so we computed robustness. We averaged robustness on 10,000 decomposition per network. So we had one robustness for each network. And we computed the predicted robustness based on b over 4. And we computed the R square of this relationship. And we ended up with an R square that is 0.68. So still quite good for such a simple equation. And so we're like, okay, so this means that we can put that on a diagram here. So basically, the relationship between the number of links and the number of species is impacting the mean number of species lost. That is impacting robustness. And therefore, we can, in fact, make a direct link between the number of species and the number of links and the shape of the two and the robustness. And why do I keep here the mean number of species lost? Because in fact, this equation allows to predict the mean number of species lost that has been used by several studies for computing robustness. And it also allows to make link with other studies that I just cited here, where you have, for example, the extinction area, the extinction slope, all those things that are based on the graph as of the number of species removed and the number of species lost. So here we can, in fact, merge more than just robustness and local stability. We can merge all those different measures of robustness. Okay, so just this said, if we go back to the expression of robustness, you can see here that we have the robustness at 0.5 is b over 4. And the highest robustness you can have in this case is, in fact, 0.5. You have to remove 50% of the species to lose 50% of the species. That means you have never secondary extinction. If we say that robustness is 0.5, then you can see that b should be 2, right? So basically, we should have, if the systems try to be the most robust to species removal, they have to be all fully connected. And obviously, we don't see that in nature. And one of the explanations for that would be that species removal is not the only disturbance that species have to face. They also have to face, for example, small change in species densities. And that's why we're going to today also look at local stability. So for the local stability, we used the equation from Alicina and Tang 2012 for the trophic networks. And here you have the R lambda max, that is the real part of the rightmost eigenvalue of the community matrix at equilibrium. And what you can see is that this value is given by various parameters, but the one we are going to look at today is S and C. C is the connectance and is a function of S and L, and therefore a function of S and B. And then you can express C as a function of S and B. And then if you do some math, then you end up with this relationship where the R lambda max is proportional to S to B minus 1 over 2. Note that when R lambda max increases, local stability decreases. So this means that when S increases, local stability is going to decrease, and when B increases, local stability is going to decrease. This is not new results, because we know that when you increase the species richness, local stability decreases, and when it's more connected networks, the local stability decreases too. However, what is interesting here is that we have the same value of B in the equation of the linked species relationship and in the equation of robustness. And you can find this expression for trophic networks, but you can also look for an expression of R lambda max in mutualistic networks. The equations are not the same because it's not the same type of network. And you end up with this relationship where R lambda max is proportional to S to B minus 1. And what you can see is that the difference, at least, for structural parameter, is that you have here a divided by 2 that you don't have here. And what is interesting, as I said, is that B is in the equation of robustness, and basically B is 4 times the robustness. So based on these equations, you can in fact predict local stability based on robustness. And to do so, we looked at the robustness average on 10,000 decomposition per network, as I just said. And for local stability, what we decided to do is to create random matrices of interaction strength and then multiply them by the adjacency matrix and put -1 in the diagonal. So basically, we did what Alicina and Tang did in 2012. But here, the novelty is that we can replace B by robustness, and we can therefore directly predict local stability by robustness. And when we do so, here is the kind of graph we get. And what you can see is firstly that there is a negative relationship between robustness and local stability, because when you increase robustness, local stability drops quite fast. And this is due to the fact that you have here the B in the exponent. So when you increase B and therefore robustness, you decrease local stability. And what you can also see on this graph is that you can have a cloud over here and a cloud over there. And when you put colors on this graph, what you can see is that it corresponds to the two interaction types. And this is because we have this divided by 2 over here that we don't have over here. So basically, the B value, well, the robustness between, the trade-off between robustness and local stability will be stronger in mutualistic networks than in trophic ones, because here we don't have the divided by 2. And we decided to test if our equations were working. And when we use our equations to predict local stability based on robustness, here is the R square. So we still quite good R square. So we do manage to predict local stability based on robustness. And what we can see, as I said, is a trade-off between robustness and local stability, and that this trade-off is stronger in mutualistic networks than in trophic ones. Okay, so we can put that in our diagram here. So basically, robustness and species richness impact local stability, and differently based on the interaction type, because we don't have the same equation in trophic and mutualistic network. And so we kind of have a clue about the question asked by Cohen and Briand by saying, okay, we have this relationship between L and S, it's network specific. We have the value of B, we can predict how the number of links changes when the number of species changes. We have a clue about the question asked by Donahue, because now we can predict local stability based on robustness. So kind of the stability dimensionality is kind of reduced, because we know that they are really well correlated. But we still kind of lack a little bit info about the local stability and how complex system, well, at least a large system, will be stable. And what has been hypothesized by May is that if you increase the number of species in a web, then the connectance and therefore the number of links in the web has to decrease if you want to maintain the same eigenvalues. And because we have different equations for the eigenvalues between the different interaction type, we kind of can look if indeed we see differences in how the number of links is shaped with the number of species based on local stability. And so we can ask the question, does stability constrain network structure? And if you do so, then you can look at the distribution of the value of B between mutualistic and trophic networks. So mutualistic are in blue, trophic networks are in red. And what is kind of obvious, but we also tested it obviously statistically, is that the variance of B is lower in mutualistic networks than in trophic ones. So you can see that here, the values of B are kind of all over here. And then for trophic networks, we are really spread along the B axis. And we were like, okay, can this be linked in any ways to what we saw for local stability, or is it just a pattern that arises for no reason that we can find, at least? So we looked again at the equation about local stability, and what you can see is that here, as I said, we have an over 2 that we don't have here. And this means that when you're going to have changes in the value of B in mutualistic networks, these changes in the value of B are going to have a bigger impact on the eigenvalue and therefore on the local stability of mutualistic networks than trophic networks. So basically, let's say I have a given eigenvalue, a given number of species, and then I increase this number of species. Then you can see that here, the value of B in the mutualistic case is going to have to decrease less in mutualistic case than in trophic network to compensate the increase of species richness. And we were like, okay, this works mathematically, but is it indeed what we see in our data set? And what we computed is the covariance between B and S. And what you can see is that it's more negative in trophic networks than in mutualistic ones. And so indeed, we have this correlation between B and S. And in fact, we find here results that were already described for connectance by Thébault and Fontaine in 2008 and 2010, where they showed that for trophic networks, when you increase species richness, you have to decrease connectance faster if you want to maintain local stability compared to mutualistic networks. And here is what we have, because we have to change more the B. In trophic networks, we have a wider distribution than we have for mutualistic case. And this analysis of the variance of the value of B, the covariance between B and S, and all those parameters that we can compute just based on distributions, for example, is possible because we have a network-specific approach of the linked species relationship. If we were working with the classical across-network approach that I introduced at the beginning of this presentation, where you have here one dot is one network, and then we make a regression through all these dots, you would have one value of beta, we call him we call it now beta to not confuse it with O on B. You would have the slope here, beta, that would be 1.311 in the trophic case and 1.318 for the mutualistic case. And then you can see that, well, how can we do, can we find pattern? Is this when you have just two values, right? And so, but this is the classical approach, and we wanted to know if our approach can be linked to the classical across network approach, and it can. Here is the beautiful equation that you can find. And in this equation, you have different parts where basically we express beta, so the slope of the across network regression, as a function of different stuff. And the first important term here is this term, where you have that beta equals the mean B. So by B here, we mean the network specific B. So basically beta is how on average in our data sets, the number of links is going to change with the number of species. And this is what people have been interested in. But you have also other stuff in this equation. For example, you have this part of the equation where you have just information due to the data set you're using, basically information about the number of species you have in your network on average, and the variance of the species richness in all the data sets, the network you used in your data set. And then you have kind of mixed terms that can either contain trends or kind of noise due to sampling effort and this kind of things. And so here you can see that the beta that is used since the 80s is in fact made of what we want, in fact, and other stuff. And this other stuff can be cancelled out, in fact, if you sample a really different number of species. So basically, if the variance of log S is really high, then all this is kind of cancelled. And then you have an equivalence between beta, so the classical across network approach, and the mean structural network property. But having a network specific approach allowed us to make this diagram and to add this little red arrow here, where we say that when the number of species increases, then the number of links, well, the relationship between the number of links and the number of species changes. And so therefore we have here kind of clues to the three questions we asked at the beginning of this presentation, and all this thanks to this simple equation that we found by reinterpreting the link species relationship. And this allowed us to connect ecosystem structure and stability. And we're back to my title, which means it's the end of the presentation. Please, if you have any comments, any questions, go ahead. I thank you very much for your attention.
Thank you so much, Camille. So if there are any questions, the floor is yours. Please, if you want to ask a question, just use the raise hand function on the participant list, and I will be checking that through. Yes, Axel.
Sorry, I'm fighting the technology here. Camille, so yes. I don't know if you can see me. Can you hear me?
Yes, perfectly.
That's all I need. Thank you very much. Yuri, please cut me off if I talk too much.
I will mercilessly.
Okay. I mean, I loved your talk because you're very good in explaining the problem, but I'm not happy about your solution.
Perfect.
And there are, one reason is that this whole idea that there is either a link or not a link is very dangerous, and I think it's wrong. So if you look at empirical data and see if there is any end to the number of links you find, if you just sample long enough, you will see there is no end.
Yes.
The number of links you find kind of decreases, and I think as a power law with a sampling effort, but it never ends. And you can reverse this problem and look at it and ask, okay, maybe there are some weak links and strong links, and what is the distribution of link strengths? And you find the links strengths, or at least contributions to the diet, which are much easier to measure. Contributions to diets follow a power law distribution. And the smaller contributions you consider, the more you will find. So this whole idea that there is either a link or is not a link is not empirically supported. And you can overcome this by looking instead at dietary diversity, say, or if assuming like if you develop a diversity measure and then then you ask maybe, okay, if all links had the same strengths, which diversity measure would this correspond to or so. So you measure data diversity, and if you do this for empirical data, then you find data diversity is constrained for trophic networks in a very narrow range. So we measured the Gini-Simpson data diversity. We found it's always close to 0.6. And for fish communities which are species rich, and for fish communities that are species poor, and we looked also at other systems, it's always close to 0.6. So in this sense, the corresponding roughly to 2 equal links. So in this sense, the number of links doesn't change with the number of species. And the other problem is once there are weak and strong links and important and not so important links, the whole idea of this topological approach, of course, falls apart. Because we know, of course, that the very weak links don't matter, but in your approach, you can't distinguish them. And so I was skeptical about this whole way of looking at the problem from a topological point of view. Yes. And there is work that based on the idea that link strengths vary, there's just weak and strong links that develop all this problem of links, relationship between complexity, stability, robustness, what happens if I remove a species. All these questions have been answered in this other paradigm. So I think you worked well within the paradigm that you set out to, that there are either links or not links, but I think the paradigm is wrong.
Yes.
Thank you.
So there is a lot to answer to in this. I think in theoretical ecology, we have to always decide on which paradigm we're going to start working, because we need to have kind of a ground to start building on. And I agree that you can indeed completely switch from paradigm. However, I would say, I'm counting the things I'm going to say. I think I'm going to say 2 things, maybe more. We'll see. So the first thing I would like to say is about, in fact, these interaction strengths, and indeed the fact of taking them into account or not taking them into account. And I think that it's kind of like in this approach, in the topological approach, what we do is assuming that when 2 species are linked, they in fact depend on each other for the survival, right? Because when you're going to remove a species and it has not its link anymore, then you consider it as extinct. So it was depending on its neighbor for its survival. And I think that maybe instead of looking at strong links and weak links, maybe the real question is about look at the links that the species needs to survive. Because maybe it will, for example, have a weak link with one species and a really strong with the other one, but the weak link species is still important because it's the only way it will get that nutrient or this kind of things. And so I think that the question is more about assuming that we have species that depend on the neighbor for the survival. If they don't, then it's okay to just look at weak or strong. But then I agree, it doesn't make really sense. If species do not depend on each other, then it does make sense. It does not make sense to say when it doesn't have its neighbor, then it's going to die because they don't depend on each other. But maybe looking at, like I said, the importance of the link for the survival is important. And there are some work that has been done on stochastic models where they used this fact of relying on the relationship for the survival. So for example, you could say that plants that self-pollinate do not need its pollinators to survive. And in that way, who cares how many links it has because it can self-pollinate. But the fact that a species might self-pollinate is viable in one community. So it's okay for one community, but on the long term, if you want genetic diversity and you want the species to maintain itself, it needs the other species and the pollinator to kind of last, right? So I would say that there are some links that are needed. Now, I agree that what I did in my analysis is considering that the data set I took, all the links were needed. And that, I agree, is probably difficult, and knowing if a link is in fact essential for the survival of species might be really difficult to find. And that I totally agree with, that it might be different at this point. But what I think is more important is looking at really how the species, like I said, how the species, what are the species that the species needs to survive on the long term. So that would be, I don't know if you agree with me or not, because I talk a lot. But
well, I would even disagree on the possibility of carrying out this definition, because in a complex network, and if you put lots of species together, you'll have some which are very abundant and others which are rare, which are very close to extinction. And now it's can happen, and it's not unusual at all, that you remove one species from the net, an arbitrary species from the network, and the species which is very rare, very close to extinction, just gets perturbed a little bit and is kicked out of the system and goes extinct, even though it's not linked to the species directly at all, just through indirect interactions. And so this question, like, do I need this one species to survive, is very, very difficult to answer.
That I totally agree, that the topological approach does not, at least so far, take into account indirect link, and therefore is kind of difficult to. So basically, the scenario we give is the best case scenario, right? So it's a case where this we can say, and this will happen, and maybe you will have other secondary extinction, but we are the best case scenario, kind of.
Yeah, just okay. So just the one point I want to make is this all has been worked out. It's all understood.
What do you mean on empirical networks?
Yes. Or this question of the link species relationship is that it's links proportional to number of species. We know this. How to measure this properly, taking artifacts into account. How to account for the fact that there are weak links and strong links. How to account for the fact that there are species are lumped together in networks, which messes up your statistic. And then using this information to look at diversity, stability, and all these things, all worked out.
But with an approach that is based on multiple networks, on looking at multiple networks, or you mean inside a network, like I suggest here, that we look at the relationship between the number of links in one web and not across different webs? Because I agree that across different webs, you have. It has been, but you have different values of A and B that has been found, and different relationship that has been found. But I haven't seen, but maybe because I didn't look further enough. But I haven't seen any paper that was in fact looking both at the number of links variation when you remove species and the number of species and how it changes when you remove species from the system.
Yeah, I think within what you do within removal of species is, I think, maybe not done so often. Because the question, because the idea is probably why it's not done is because once you remove plenty of species, typically these networks become more robust and more stable, and then it's not so interesting.
But what is interesting, and it's the results that I still need to understand, in fact, is that the B value does not change along the decomposition process, right? It's the same. So if we take, I'm just gonna talk about something we can see. So if we take this graph, you have the number of links and the number of species, and you have the relationship between the two. You find one value of B that allows to predict this whole decomposition process. So the general idea is that the value of B won't change along the decomposition process. But because B gives the robustness, it means that the robustness of at least in this approach, the robustness doesn't change in a smaller network than in a bigger network. It's still the same robustness. While the stability, so the local stability, I agree, will change because you change S. But S does not appear in the robustness definition. It only appears in the local stability definition. So
what you could try is build a food web with population dynamics, where abundances kind of are controlled by the trophic interactions, where there's energy conservation, dispersal, and all these things, and then you will see how much is left over of your approach. And I think it won't hold water, but you can try it.
I agree that it's a topological approach, and as soon as you get interactions trying to account, it might change the results. Yeah, but here it's really the removal of species per se without knowing.
Yes, no, as I said, within the paradigm, I think it's interesting and impressive how far you've taken it.
But you make a good point, and I will think further on this to see how this affects. Because in fact, what I've been looking for also about this detection of the number of links is that if B doesn't change, then we could be able to predict how the number, like with ALF, the network, only sampling 50% of the species and their links, we could maybe predict the full network. And this is something that I've been working on, and I haven't really the clue. I've done some simulation, and it seems to work. And so that would be also something that I would like to compare with the effect of just, for example, like you said, sampling only strong interaction or weak interaction too, and see how we can or not predict this. So that would be really interesting, like you say. Yeah.
Yep. Okay.
Thank you.
Okay. I'm sure there are other people who have comments.
Yeah, so there's actually a question in the chat from Imam Ben Ammar, who says, sorry, I'm in a noisy environment, but my question is, as a biologist, I know that some species are able to adapt. What can happen if the remaining species create new links in reaction to species removal?
Exactly. So this is an important also hypothesis of this. We assume that there is no rewiring. So we assume currently that we indeed have a power law, so that when you increase the number of species, the number of links is going to increase, and when you decrease the number of species, the number of links is going to decrease, right? And this is kind of a strong assumption, and I agree with that. That when you remove species, maybe you can say, for example, it has been shown on the field that when you remove the pollinator, for example, then all the pollinator will have a bigger niche afterwards and interact with more species afterwards. So this is not taken into account in our model. However, you have some studies that says that if you sample long enough on the field, then this interaction that is going to arise because of adapting behavior should be in the matrix you're analyzing if you sampled for long enough. At least you should have seen once. And we go back to the question we had just before about the interaction strength, where you say, okay, this link has been seen once, so it exists. Now, when do we take it into account or not? Currently, we just said we take all the links into account, but you might want to do various scenarios where you say, based on the frequency and the importance of the species in the diet, for example, we're going to kind of make different simulations and see how it impacts or not the results. But I agree that we don't take rewiring here into account, but if the studies has been done on a long enough time, we should have seen at least one occurrence of that link. Is the answer to the question. I don't know if it answered the questions.
I'll have to look in the chat. It says thank you.
Okay.
Are there other questions? Please feel free to chime in, raise your hand in the participant list. While we're waiting for a question, I might ask something. You talked a lot about various R-square values, I guess goodness of fit measures. And in particular, not for this one that you're showing, but a little bit later for the robustness.
Yes.
Values, even later, actually. Sorry, I should have said the relationship between robustness and local stability. You said something about R-square values there.
Yeah, I said S-square is 0.7.
Probably know by heart, but I don't. Yeah, exactly. So exactly. And you mentioned that they're sort of lowish, but still okay. I would maybe just to strengthen the message, we don't really care about these R-square values, do we? I mean, the point is the negative relationship between them, and of course it's going to be very noisy. But the relationship itself is very clear. So even though maybe the R-square is not so strong that you could numerically very well predict where these fall, but you could predict the region in which these.
Well, this is the issue with robustness, for example, because when you have 166 species, for example, you have so many possible decomposition based on the level of the order with which you're going to remove the species, that you have to do a lot of decomposition to find kind of a trend. And this is why here what matters is not, well, the R-square is to just show that it works, but the general idea is indeed, like you said, that local stability drops with robustness, and it drops faster in mutualistic networks and in trophic ones.
Exactly.
Yeah. I agree. And also for local stability, if you change the interaction strength, I mean, there is other parameters than just the structure in these equations, right? So obviously those are going to impact also the results. The general idea here was just to focus on the structural parameters, so S, C, and L, and therefore B. Yes.
Mm-hmm. Thanks. In the meantime, Geza has a question.
Okay. You have questions about each other's paradigm already. So I try to tell a third paradigm, and my doubt about both of your paradigms is that if we look the May type of stability analysis, the very most stable ecosystem is when the number of links is 0, and then I'm not sure whether this is a good result. And in your case, of course, it is not true, because you postulate that everybody needs somebody. Then your optimal case is that species are exist in pairs.
Yes.
Anybody has a single link to somebody else and nothing else.
Yes.
And in this kind of paradigm, the interactions are something wrong, which destroy the stability of the ecosystems.
Yes.
And my feeling, and I don't know how to implement it mathematically, but my feeling is that the interactions present in most of the case to help at least one of the species, maybe on the cost of the another species, but these things that the minimal interaction would be the most stable is something wrong starting point.
Yes. So if I understand what you mean, is the general idea is that if you have only specialists in your network, they're going to interact strongly, and therefore the mu is going to be high, and therefore we're going to have a less stable system, right?
Yes.
Okay. Yes, I agree that it's what we found, and the general idea, because we looked only at structure, and obviously there is not only structure. Because we looked at the structure, the general idea is that the eigenvalue, well, the local stability is going to be lower when the perturbation can spread in the network. And obviously, when you have only specialists in your network, the perturbation cannot spread. And that's why it's the most stable one. Even though the interaction strengths are really, really strong, the general idea would be that the two species are not gonna the perturbation is going to stay in those two species and not spread in the entire network. But I agree that in the equations of May and Aresina and Tang and others, you have indeed this mu, and this is back again to the fact of taking into account the interaction strengths. And maybe there is another layer to this, because for robustness, for example, if you have those really strong interaction, then because here we consider that the species do not go extinct until they have no resource left, but you could say that they go extinct when they have only 70% of their resource left, because they needed the 30% left over. And then this is where you're going to go closer, and I think go closer and closer between local stability and robustness. And at the end, maybe the negative relationship might in fact inverse itself, because if you change the threshold at which the species are going to disappear. So basically, I can maybe explain this based on, where is it? I had a slide for this, yes. So basically here, I'm going to try to show this. So basically what we said is that species compensate. In our analysis currently, we say that the probability of species to go extinct is 0 until there is no resource left, and then the probability of a species to go extinct is 1. But if you move the threshold, and you don't say you have to lose 100% of your species, but let's say, for example, 70% of the species or 30%, etc., then you end up with this kind of graph where it's a little bit tricky to see, but the general idea is the extinction threshold. So you're going to say, I'm going to say that my species go extinct when it has only 80% of its resource left, or when it has only 60% of its resource left, or 40% or 20%, for example. And what you can see is that the robustness is going to change. So here in blue, you have high value of B, in red, you have low value of B. And what you can see is that, in fact, you have an inverse. So the relationship between robustness and B changes if you change the threshold at which you're going to consider the species extinct. And as soon as you are lower than 0.5, then you have a negative relationship between robustness and B. And this is because when you're lower than 0.5, you're going to assume that being well connected is a problem, because then you depend too much on all the species you have. And as soon as you lose a species, you're going to go extinct. And by doing this, we kind of go closer to local stability. And I think the next step in this work is really to understand how we take into account the interaction strength. And can we do that? And going from a full topological approach to a non-topological approach, and even a dynamical approach like local stability, how can we link all the things together? And I think this is possible by having a solid ground where we say, okay, we know now when we don't take an interaction into account how it works. Now let's put some interaction strength in it and see how all those conclusions changes. And I agree, then we will have probably different solutions than what we find currently. Currently, it's really like a base to build on. I don't know if I answer your question again, because I get lost in what I say, and then I don't know if I answer questions.
Lisa?
It's okay. I don't know how to implement what I wish to say, so
I don't know yet either. But
okay. So
I know how to implement the threshold. I know how to find an equation for the curve I just shown. I'm almost there. Okay. But then here it's still a threshold and not really interaction strength. So the next step would be to go indeed with interaction strength and modeling like a real dynamic systems where we would remove species and see how the dynamic changes afterwards, because here we just see how the graph change afterwards.
Okay. We'll see.
Okay, thank you. Are there any other questions?
If there is no further question, then I'm saying that Stephen Elmer is the next lecturer 2 weeks from now. And we have a few persons who told me last year that they will be ready to talk this semester, and I will call them about the dates. And otherwise, I'm happy. We are happy to hear any suggestions for further lectures. And Chris, tell us how long our list are now. I think there was 42 people here today, and otherwise.
I don't know if there's much to say really, other than that, yeah, it seems to be growing well. We've got about 200 people on the email mailing list now, and quite a good number of people following the Twitter and so on. But it's always helpful if people pass on to sort of their local networks that these seminars are going on, so we can keep them as large and productive as possible, for as long as possible.
Okay.
Okay, let me know if anyone has any other comments. If not, then thank you so much again, Camille, for your presentation, and thank you for the discussion. In that case, thank you. Have a good evening, and we want to see you all next time in 2 weeks for Steve Elmer's talk.
Okay.
Take care. Bye.
Bye. Thank you.
Bye.